Here from video, not from the choose out.
Video settings. I don't have all.
Oh, because it's not connected.
Do you think it will appear if?
Yeah, yeah, yeah.
Okay, that's a shame. It seems like a part of a setting. So that's USB, so it goes here. On this side.
Okay, let's try it. We have to.
Meetings are. No, it's here. No, it's face this. This. Right? Oh, no, it's automatic. Yeah, speaker and mic.
See that.
Perfect. Oh, just I can just.
From Zoom.
It seems like it. I can just flip like this, right? I'm gonna advertise our. So don't. Oh, no, but, okay, so also here. Well, it's so this is very useful device.
Good thing you have it.
Okay.
Yeah, make a few announcements and things because.
I got a message from Conquem, the effect that every time I looked over to that board, she couldn't hear me. So probably you don't intend to do that.
I don't.
Maybe useful to stay in the center.
Yes, and the probably operation.
Probably in this, right?
Maybe it's this one. Oh.
Yeah, if you want to talk, you have to take this one. Yeah, I'm not gonna do that.
Doesn't seem to have any.
Think about it.
Hello. Hello.
Louder.
One.
Louder.
Looks like a flash. One.
Louder. Now game two.
No, it's okay, Joe. All right. And if I stay here, this is nice.
You don't need it. This will get in.
Yes, but I have to split slide. Right? So,
This. Strong enough.
so what should I say to her? Flip the slide. I need to flip the slide, right? So I need to go from one to another.
Oh, you have a voice control thing?
No. I can just, I want to do it here, so I do both the
I think, but you don't. That's what I'm.
I might.
No, because this one.
Oh.
Okay, let me make say a few things. After Timur's lecture, there's dinner, but the dinner will not be here tonight. It will be down in the biosphere. Okay, so which means that for those of you who are presenting posters, you should take your posters with you as we go down. Because it's a bit of a walk, especially at night, to come up. So take your posters down, because then we will put them up and there will be refreshments and things for the poster session, courtesy of Lucas. So, so this you should keep in mind. You go down after the lecture for dinner. I think it starts pretty much right after the lecture. Number two, oh, I should ask, Jacqueline is actually, I noticed that she's on. She has shared with everyone, with the students, all of the email addresses and names and things of everybody, right? Okay. So that you're in touch with each other. Number three, for Wednesday, we will not be going for a hike because any of the number of forecasts that you look at has either high winds or rain or snow. We probably will get some snow up here. Okay. So what we will do is that we will switch around a few lectures and on Thursday afternoon, we'll go for a hike, which at least right now promises to be a much better day for hiking. Okay. So Wednesday, we will probably have a lecture in the evening because we will not be going for a hike. I will announce it tomorrow, and in place of Thursday when we go for a hike. So, without further ado, lecture 1 by Timur.
All right, do you have a question, Hassan? You have a question.
Oh, when do we expect the recorded videos to be on?
So, I will need to talk to Jacqueline. I mean, it could be put on daily, but on YouTube, because she has to create a playlist that she can just this and that one. So, yeah, so maybe on Wednesday we will have Mondays. So let's say that 2-day gap or 1-day gap. The slides. Yes, that's a good point. We have not done it. I'm going to write a note to Jacqueline. She can create a drawing. But it would be not in the lectures, we drop their slides in there, which I assume we will all be more than happy to. Okay, good.
All right, so, okay. Hi, everyone. So my name is Timur Tscherbul, and I'm going to talk today about molecular structure, right? So this dreaded topic. So I'm from the University of Nevada, Reno, and we're also in the mountains. So I didn't feel like I left ever. So, and we have very similar settings. And if you're interested, we have a MS and PhD program in physics. So if you have a friend who is interested in this mountain stuff, so and doing physics, please let them know. So this is my kind of like summary of what we already heard. In fact, most of it we already heard from John. So molecules are ensembles of charged particles. So they are incredibly complicated. There is electron spins, nuclear spins, flowing around, right? There is charge currents, there is spin currents, there is interactions between electrons and nuclei, there is relativistic effects. There, it isn't even possible. It's actually a miracle that we actually don't really understand, that actually we can understand this system. So, and I'll try to prove this point in the next couple of slides, or actually 10 slides, but
Can you maybe minimize that bar?
I can try. But it's still, I can move it around. Yes, right? So electrons and nuclei. So how do we go about describing this? So the total Hamiltonian seems like a not so difficult, right? So there's electron kinetic energy. There's the part that's due to the electrons and due to nuclei. This little I refers to electrons. The capital R's in this particular slide refer to the nuclei. There is interaction, Coulomb interaction, right? Charged particles, non-relativistic stuff. So there is no, spinors in there. No spin is included here, but because it's non-relativistic Hamiltonian, there is interactions between the nucleus and electrons, and then there is this the term on the right. So there's a mass polarization because it's a small correction because we switched. So we have to choose a center of mass, and usually the center of mass is chosen to be the center of mass of the nuclei. But it should be, the life is easy when we choose it at the center of mass of the entire system. And because it's these two centers of mass are not the same, right? And there's a lot of electrons. They're shifting a little bit the center of mass. There's so-called mass polarization correction, which mostly we're going to ignore. But there's also nuclear kinetic energy and nuclear repulsion, the last two terms, right? So we see that the Hamiltonian is kind of like, you can kind of understand that, right? Take an undergrad E&M, that's all you have, right? Except instead of kinetic energies, you have, del square operators. That's just where quantum mechanics comes in, essentially, as far as molecules go, right? So, and what we're going to do, we're about to make it way more complicated, right? Because this Hamiltonian is not very helpful. Because first of all, it's not kind of clear where is rotation there? Where is the potential energy surfaces there? This is the most generic Hamiltonian one can write, right? It doesn't follow. So all the molecular physics is, in other words, an art of simplifying Hamiltonians, right? So what we're gonna, so this is a good starting point. So what we're gonna do, and again, John described it already in detail. He was actually still almost there. We're rotating the coordinate system, and the key terms to understand molecular physics is nuclear kinetic energy. The nuclear kinetic energy is del square operators and nuclear coordinates, right? And or you can write p square over 2 mu, and a mu is a reduced mass. So this operator is expressed in lap or space fixed frame. So the capital X, Y, Z are the unit vectors along the corresponding Cartesian unit vectors, right? So we want to transform it to a frame which actually rotates with a molecule or body fixed frame, or molecule fixed frame, which we do using LRAs, right, as John has described. So this is just a rotation matrix, but it has dramatic consequences for everything, because together we cannot just rotate just the nuclei, right? And then together with the nuclei, we have to rotate everything pretty much. And that's where all the interesting physics comes from, mathematically. So, however, before we get to that, I just want to emphasize how the rotational kinetic energy, one of the most important energies for molecular physics, transforms under rotations. And again, John covered that mostly, so I'm not going to spend a lot of time here. You can do it in two different ways. And so you can say, okay, I'm going to rotate everything to the molecule. Electrons, nuclei, everything. Electron spins as well as electron orbital motion, everything. And in this case, we get this Hamiltonian, which is so-called Hans case A. It's called Hans case A, where everything is in the molecular frame. So we define capital P with the sum of L and S, or electron orbital and spin angular momentum, and then we get this operator that looks like J minus P squared. J minus P squared, and we can open it up and get this J plus P minus J minus P plus. Again, John talked about that. So, okay. So kinetic energy is very interesting, right? So this operator J minus P depends not only on the nuclear coordinates, but now because we have made the transformation, it actually depends on the electronic part of the topology function. So this Hamiltonian, so it's funny, right? The nuclear kinetic energy is not really nuclear kinetic energy. It actually depends on operators Px, Py, Pz that actually contains electronic coordinates. This is the essence of Hans case A, and you don't have to do that if you don't want to do that. So there's Hans case B. So, okay, there's a lot of things, right? So if you don't want to select the time, you apply an external magnetic field, and in that one, sometimes you don't want to transform electron spin along with the molecular frame. So you want to stay, you want to treat the spin separately, right? You care about it, so you really can handle it carefully. And so in that case, you just transform only orbital angular momentum of the electrons, which is always a good thing to do. And then you get Hans case B in this case. So it's really as simple as the difference between Hans cases is what do you transform it to the molecular frame, really. Electrons spin, are you doing it or not? Okay, so all right. That's kind of like the remarks, and really remarks on top of John, what John already covered. Now, what I'm gonna finally say is that this operator, yes. Yes, there are Hans case E, I think D and even E. E is when you don't want to bother. You don't never transform anything to molecular frame. It's called Hans case E. But it's very rarely a good idea. It's a very good idea when your molecules that look like separated atoms, like van der Waals molecule. In this case, Well, I mean, I just better describe it as two separated atoms, like Feshbach molecule is a good example. That's where you use constant E. But it's a rarity. Like C is like when spin orbit, like you instead of elements, you couple them and then you deal with total electronic orbital and total electronic angular momentum, because you cannot define L and S in the relativistic case because there's strong spin orbit interaction. Constant C is also pretty rare. It's used for molecules like I2, iodine, which looks like it's the most well-known example. Or another case, it's like similar to LS versus JJ coupling cases. So, but yeah, that's kind of, I'd like to leave it at that because A and B is overwhelmingly, overwhelming majority of cases, right? So I just want to point out this interesting, that's what I was saying about Hansky. But this is the components of, and maybe John mentioned that, but the components of the total angular momentum in the molecule fixed frame, they are weird. They're not normal angular momentum. They satisfy so-called anomalous commutation relations, which means that if you just commute them, you get this minus sign, which is inserted there, right? Which is like anti-commutation. So it's not like a normal Lie algebra that you get for space-fit component of angular momentum, and then instead you get this weird minus sign. So you have to be careful when doing the matrix elements, relative matrix elements, involving anything that's related to the molecular frame. But once you're aware of that, you typically have rules, and textbooks like their textbook or Brown and Carrington, they warn you about that, and they warn you how to work with that. So again, we're not going to go into detail. This is mostly for molecules with parity doublets. This is important for Hansky C, for KRB, alkali dimers, and double sigma molecules. That's not an issue, right? So, but it's good to know the commutation relation. So these are not really, they're kind of posing as angular momentum. They're not angular momentum. So that's about Hansky's B. I said everything about that already. So now let's review the Hamiltonian of a diatomic molecule. That was just purely for fun. I found it in Brown and Carrington, and so I'd like to actually go over all the terms with you so that we can appreciate the complexity of diatomic molecule. So it has 32 terms. So this is after we rotated everything, electrons and nuclei into the molecular frame. So that's Hansky's A. So that does not include nuclear spin. Okay, so this is just like electron spin, like and rotation, and the effects coming from separation of rotation. So we see. Let's begin. There's translational kinetic energy. The molecule moving right through space. We separate it out. PO, the center of mass motion, is there. There's kinetic energy of the electrons. Okay. There is mass polarization. We just mentioned that because we choose center of mass differently slightly. Then there's relativistic correction to the electron kinetic energy, right? Because of course electrons are moving pretty fast, so we have to correct for that. And this is the next leading order, right? So V squared and C squared. Okay, then you see these blue boxes. This is what we already covered, and this is what John covered. So I'm not going to talk much about those, right? Rotation, vibration, we all know about that. So, but it's not all. There's electrostatic Coulomb interactions again. So this is pretty familiar. Coulomb repulsion between the nuclei, where it starts to get interesting. Darwin type correction to the Coulomb potential. Again, a relativistic correction. Spin orbit coupling, maybe familiar from atomic physics. Actually, all these terms should be familiar if you're taking quantum 2 at the graduate level from Crane to Nuji. You go into details of this Darwin term, spin orbit coupling term, and other terms, right? But some of them are uniquely molecular. We're going to emphasize that. Spin other orbit coupling, that's weird. It doesn't exist in hydrogen atom because there's no other orbit to interact with. But this actually exists in 2 electron atoms, at least with 2 electrons, because there's a spin can interact with its own motion, but it can also, because it interacts with currents induced by the motion of other charged particles, right? So with other electrons as well. So that's called spin other orbit coupling. And those, by the way, these wedge signs is just essentially a crossroad. So this is the weird way Brown and Carrington, decide to go about crossroads. Yeah. Okay. Now there is orbit coupling. I'm sure you heard about that. It's the coupling, due to charge currents, due to orbiting electrons, right? Mass polarization correction. Okay. All right. Spin interaction. So this one is important. This one is between two electron spins, a magnetic dipole interaction between two electron spins, right? It's there because they're magnetic dipoles. One spin is creating some magnetic field interacts with the other one. So that's kind of typical one. Also exists in helium, for example, right? Pretty common. In molecules, there's also a term that involves delta function. That's direct interaction between two spins. Spin rotation interaction. Okay, so the action of the spin was rotation, was the rotation of molecular frame, because molecule rotates, creates fields as rotating charge, and that all molecules interact. Sorry, electrons interact with that field created by rotating molecule. All right. Okay, all right. Spin vibration interaction. Because molecules vibrating, there's also moving charges, creating magnetic field interacts. Orbit rotation interaction for the same reason, orbit vibration interaction, electron spin Zeeman interaction. That's when you put a molecule into a magnetic field. There is, of course, all the electrons start to respond to magnetic field, but that also gets corrected by this, first order correction in a weakly relativistic limit. So orbital Zeeman interaction for the same reason, all this orbital motion interacts with external magnetic field. A relativistic correction to the orbital Zeeman interaction, translational Stark effect, rotational Zeeman interaction. Those three terms, Brown and Carrington don't even name because there isn't a name for them. So I actually just wanted to emphasize, it's quite interesting. Small Zeeman terms, they call them. But it's not clear if these terms, if anyone has ever worried or considered those terms. So here is plenty of opportunities for research on the atomic molecules for you guys. Translational Stark effect, because as the molecule is moving, right, if you have a molecular ion, it's moving, it creates a magnetic field. And, that interacts with external, magnetic moment acts with external magnetic field. So fortunately, in neutral molecules, we can neglect the term, and that is the term that John considered in detail. So I'm not going to talk about that. Electric dipole interaction, electrostatic interaction, again, charged molecules only. And finally, diamagnetic interactions, because when you consider rigorously the interaction with magnetic fields, you introduce vector potential and have the speed of a Hamiltonian, right? And then you open up brackets, you have A² terms, and they also show up, of course, because they should be there. And pretty much the conclusion, I don't want you to remember or even, but it's good to reflect sometimes that, everything interacts pretty much with everything in molecules, right? That's first conclusion. And then there are very few interactions that are absent in molecules.
It's only electromagnetic.
And with relativistic corrections.
With relativistic.
With spin, yeah.
Yeah, but not weak interactions or something.
No, nuclear spin not included, weak interaction not included, QED is not included. Yeah, so actually it's a good point. I have to, the assumptions are quite, so does not include nuclear spin, and it based on Dirac and Breit equations, so for 1 and 2 electrons. And so QED corrections are not used, although but actually this Hamiltonian is pretty good. So you can describe most spectroscopy experiments done in molecular spectroscopy using this Hamiltonian. But obviously it's a complicated Hamiltonian. So we want to simplify it a little bit, right? If we can.
You say QED is not included?
QED is not included. No. Quantum QED corrections are not included. And actually I should also say non-Born confinement. Actually, Brown and Carrington are silent on that, but they're not included as well. Due to other electronic states affecting, which are very important for light molecules, actually, attaining especially hydrogen. But QED and non-Born-Oppenheimer are kind of similar.
So lamp shift or something like this?
No. No. Yeah. The most important interaction that's omitted here is probably, the lamp shift. For example, G factor, deviating from 2 is not included as well. Yeah. So, well, Dave talked about G-2 experiment. Yes.
The original Schrödinger equation that you saw in the very beginning, does not have all of these jumping of quadratic or fortic or cubic interactions. So these emerge so all this zoo of stuff that you showed, they emerge in particular situations where you bring it from all sides and
you basically rotate. Well, most of them emerge from the fact that you're rotating. You're considering a rotating frame, which is non-inertial frame. So you have,
you can go from these somehow by rotations to all of these.
Yes, and plus considering relativistic interactions. So you're considering small corrections. Yes.
Because here it's non-relativistic.
Yes, there's no spin. Non-relativistic Hamiltonian cannot depend on spin. But like here, see, we're adding Dirac equations almost silently. I didn't mention that, but we actually started using Dirac equations for some of the terms. But you actually don't even need to worry about Dirac
All
equations.
of these is essentially relativistic.
Weakly relativistic. So in heavy molecules, you cannot describe iodine with that. So you have to do a lot of more work using rigorous Dirac kind of like treatment. You cannot just say, oh, there's electron spin. There's with Dirac equations, you probably know, there's big component and small component, and you have to do the full four component analysis. So it's no longer this Hamiltonian breaks down. So this is safe to say for light.
Can you roughly say how big the individual terms are? I mean, there are 32 terms.
32 terms.
And how big, I mean, is there an ordering?
It depends. Let's say if your molecule is moving really fast.
For example, the QED, I mean, in hydrogen, QED is important.
Yes.
Here it's not important, maybe.
Yes, it depends. First of all, yes, on the charge of the nuclei and effect, different effects. I would say electronic terms that involve interaction with electrons. Here, Coulomb interaction, electron nuclear, and Coulomb repulsion are by far the large. They make up the largest.
Yeah, that's electron voltage.
Yes, exactly, exactly. Yes, the next.
I can imagine that some of the electrons that appear more towards the end
Yes.
are smaller.
In fact, I should say not all the terms are not known. I mean, many of these terms are never considered.
Because they're born, or because
I don't know, because people are probably scared about like with oh, I mean, as far as Zeeman terms, for example, I think they can be subsumed into things like diamagnetic Zeeman or that already small corrections to G factors and things like that. So there is another reason they're not considered because they're just no one would assume to calculate or would try to calculate the response to magnetic field with such a precision to delineate different contributions. Yeah. So they just like phenomenologically add them all up. Many of the terms do not survive in the end. But yeah, I mean, it's a good question. Many of them are very small, but it's very, very highly dependent on the situation, particularly molecular. Other questions?
Yes, so I mean, it's a highly non-trivial many bodies that have problem. So usually for many body problems, it's more useful to write it down in the second quantized form to also account for it.
Perfect. You can do that.
So yeah, no, I mean, it's not
Usually, actually, you're right. I mean, this is done for electronic terms, right? Like people do that all the time in quantum chemistry. Sorry, I'm moving in the wrong direction. So for those terms, you see, for example, electrostatic Coulomb interaction between pairs and electrons. This is like any quantum chemist will tell you that this is 4 electron integral, essentially, right? 4 electron repulsion integral times like 4 product of 4 fermionic creation, 2 creation and 2 annihilation operators. And people like this is how they solve quantum chemistry problems, right? Fixed nuclei, they do write that in second quantized form, and they determine the expansion, Fock, and CI and stuff like that, many body techniques, and then they all these other interactions is not advantageous because I don't know, maybe you can write anything in second quantized form, right?
Maybe adding up to this, I have no idea. I mean, this is basically solving Schrödinger equation.
Yeah.
So what I understand from him is basically you consider the electron maybe hopping around the nuclei in a kind of Fermi-Hubbard model.
No. It's just they're not local. They're free to move. In the Fermi-Hubbard model, they're sitting.
Yeah, but I can put it on the lattice maybe. And
you can put, but it will be a very bad approximation because molecules they're like free to move. It's like a gas. Like from the viewpoint of condensed matter physicists, I actually once just sent my paper on molecules to a condensed matter physicist, and he said, "Oh, this is just electron gas." So, and it was like a revelation to me because for him, like, this is what he would look at, and like free electron, electron gas in the potential of nuclei. You think of it. Yes, John.
And say chemistry is more of you guys. I think that if you choose your battles, if it doesn't electrons that matter most, and really write down how to calculate that all important.
Yeah.
I don't think it's
but it's a many-body, like Hartree-Fock method. I would say it's a many-body method, right? I would say more like.
not one very popular.
Well, yeah, you can treat it. Like you can think of it as like general. Yeah, but based on it's a mean field. Okay, so I should say it's mean field, right? Hartree-Fock. by definition. So you describe electron in an average field of other electrons, and then on top of that, you do many body corrections due to the like exact form of electron interaction. That's how, but we're getting too much into quantum chemistry. I don't want to do that. So I love quantum chemistry, by the way. I talk about quantum chemistry all the time. But they solve these three terms essentially. Yeah. But sorry, I might not have addressed your question, or
No, it's
okay, we can discuss more later. But there's too many terms to dwell on them. Perhaps one. But the point is like so we want to derive some sort of we want to be able to simplify, and this is like molecular physicists for 70 years. They figured out how to reduce this crazy complexity to a very well-defined classes of Hamiltonians that apply to different molecular systems, right? Depending on the kind of system. So first of all, let's assume that we're interested in specific vibrational and electronic states. Let's say ground states, right? Okay, that's something, right? So then we integrate over electronic and vibrational coordinates. Why? Because, well, electronic, like quantum chemists, friends, they give us electronic wave functions, right? And we can just take the Hamiltonian and integrate all out over electronic coordinates, right? So the resulting Hamiltonian will only depend on the nuclear degrees of freedom, right? And because we also integrated over vibrational coordinates, we don't want to deal with vibrations too much. And in molecules, it's easy to do because there's only in that one, just two nuclei. So we integrate over vibrations too. So in the end, we get the nice Hamiltonian. In principle, we could. It only depends on rotational and spin degrees of freedom, right? That's kind of the goal of this and the art of building the effective Hamiltonians for molecular physics. And this is what molecular physics spend their time the last 70 years pretty much doing, right? And they created a wonderful library for us. So we don't have to worry about all these terms. And they checked it against spectroscopy and all the, so we don't have to worry about these 32 terms. We just have to, open Brown and Carrington and, look at the correct Hamiltonian. But this is just gives you a kind of like sequence of steps. It's a formidable sequence of steps, which is by no means obvious. But people kind of, it's like the treasure of molecular physics. So I'm giving you like in one slide, essentially. But then you see this effective Hamiltonian is great because it only has rotation and speed degrees of freedom, right? And we can deal with that. We can deal with rotation because, well, John told us how to do that. Now, all my job is pretty much to kind of teach you how to deal with spin degrees of freedom, right? Which is what is left over after we integrated everything. And I just want to make a point like, this sounds pretty obvious and simple, but it's far from it. So, for example, this is a molecular orbital, like, for example, oxygen molecule. You have to build an electronic wave function, and basically you create some sort of molecular orbitals, right? You combine atomic orbitals, and then you put these arrows, which are electrons, and we have seen it if you've ever taken a chemistry class, right? But this is the way these orbitals actually combine from atomic orbitals. Remember, Dave talked about like S&P orbitals hybridizing in an electric field. Actually, for molecules, you get it for free. You get a molecule, you get hybridized orbitals without any external electric field, like methane, for example, sp3 hybridization and stuff like that. So orbitals can be much more complicated than molecules. But the point is that quantum chemists can take care of that. They can calculate it. It's their job, right? They get paid for it. So, fortunately. So all we have is just nice effective Hamiltonian rotations and spins, right? That's the point of kind of the first part of my talk. And most common molecules are singlet sigma molecules. Why? Because they're chemically stable. If there's an electron, so what does it mean single sigma molecules? There's no net electron spin. So it means that all of the spins in these molecular orbital diagrams are paired up. Actually, this is not an example of a molecule where all the spins are paired up because oxygen in this room has 2 unpaired electrons, but it's pretty much probably the only stable molecular radical that exists. All the other molecules with unpaired electrons, they're extremely unstable typically and cannot be found in nature and cannot be taken out of a bottle, with the exception of very few molecules like oxygen. So most of the molecules have 0 electron spin just because they haven't reacted. So you see them, right? They haven't reacted with anything with it. Now, also, coincidentally, most of the molecules that have been created in the laboratories at ultra low temperatures are actually singlet sigma molecules, because these are ground states and they have large electric dipole moments for many interesting things like quantum information science and quantum many body physics. So we know our KRB, but also RBCS right? Sodium, potassium, sodium, cesium. Now I heard about lithium, cesium. So lots of molecules are being created, and they're all singlet sigma molecules. So if we understand the structure, we'll be, in a good position. So we'll understand everything that's going on pretty much in the field of cold molecules. I should say 70%. Right? So how do we need to specify an effective Hamiltonian. So open up Brown and Carrington, or we open up a paper by Jeremy Hudson and Piotr Zhukovsky and their collaborators, and see that the effective Hamiltonians for singlet sigma state, they have 4 terms. So there's rotational, hyperfine, spin, and Zeeman terms, or Stark and Zeeman terms. Sorry, Stark term, I'm not going to touch because John told you everything about it already. So I'm going to talk about the first, second, and third, and fourth term on the right-hand side, which is rotational, hyperfine, and Zeeman interactions, with external magnetic field. So you see that hyperfine Hamiltonian has this interesting form. It has, and I'm going to explain it to you, actually, all of these terms, they actually make sense. So you could have kind of like, you could have written this Hamiltonian even without knowing all those original 32 terms that went into the original Hamiltonian. So let's try to make sense of those terms. Okay, so this, especially the first time, VI dotted with QI. What is that? Actually, this is the term which it's the most important term in the hyperfine structure of singlet sigma molecules, such as carbon. It's called nuclear electric quadrupole interaction, which sounds horrible, but I'm going to explain it to you. So then the second term on the right-hand side in the hyperfine term HHF is this interaction of the spin of the molecule, of the rotation of the molecule with its nuclear spin. Because remember, nuclear spins are not equal to 0. Both K and RB, they have nuclear spin. So as the molecule rotates, it creates magnetic field that interacts with the spins, right? And the C sub I, the rotational spin, rotational interaction constant. And the sum from 1 to 2 is the sum, actually, K is 1 and RB is 2. It's just the sum of the nuclei. And of course, John talked about rotational part again, so I'm not going to dwell on that. And also, I just want to add that there's like additional term there, which goes like n to the 4th. It's so-called centrifugal distortion. Because like as molecule, rotates, it actually distorts itself. And because of that, there is high order terms, and there's actually the entire series of terms, but d sub v is much smaller typically. So if you said d sub v equal to 0, you wouldn't make a big mistake essentially. So, but the term is there. So for very precise spectroscopic measurements, it should be there. It should be included. All right. So there's also interaction between 2 nuclear spins, right? Nuclear spins sitting in a molecule, they feel each other, right? So, because again, nuclear spins create magnetic field, and tiny dipoles, magnetic dipoles. So they create magnetic field, the other spin responds to that, right? And because of that, there's this dipolar interaction in C3, I1, dotted with T dotted with I2. And it's again, very similar to the dipole interaction that John talked about, electric dipole. Now it's magnetic dipole interaction, which is almost the same form, except that it's much, much smaller. Right, and finally, there's direct interaction between 2 nuclear spins, and then there's Zeeman interaction. So let's, okay, so I think let's talk more about different mechanisms. Actually, question.
So what do we lose going from that 32 terms to this effective Hamiltonian, and when is it going to be precise? Like, do we plug in some good constant? And
yeah, for you, it depends on who you are. So. If you're going, and maybe more importantly, what your goal is, right? So if your goal is to quickly calculate some energy levels to pretty good accuracy and use them in your simulation, then I would use the effective Hamiltonian. And the advantage is that simple form and parameterized constant. There you can look them up in a table. If you, on the other hand, if you don't know, for example, you're trying to make a prediction for a new molecule, and no one has measured it, right? Then in principle, these constants can be expressed back, like related back to those parameters in that model. But to calculate that would be a very long and tedious calculation, which would involve solving an electronic structure problem and calculating those. So you'd have to team up with probably some quantum chemists, and it's like a whole project. You have to write a grant application essentially in order to do that, right? And you may not be successful. So it's much simpler to ask an experimentalist to measure something like, and this is the thing with these effective Hamiltonians, right? But there are some situations that you cannot measure something. For example, some radioactive molecules, I think that they measure is for these kind of predictions, right? So sometimes you have to do these calculations, but these are generally, complicated calculations.
So if I'm able to measure the constant,
Then you should be fine. Yeah. Other questions? No? All right, so. Sorry, what was that? The D operator. T. Oh, it's a tensor operator that couples. It's essentially a magnetic dipole-dipole interaction between two nuclear spins. Not right. So John covered it. it may not. He might not have denoted it as T, but you know, we'll talk about that. So, but first things first. Electric quadrupole is much more important. And what is the electric quadrupole? The thing is that actually nuclei are not spherical objects. If nuclei have nuclear spin greater than 1/2, they have this like weird shape, like peanut, maybe, right? And because of that, they have like spatial extent, and so they have a quadrupole moment, right? It's not just dipole moment, but there's a quadrupole moment, higher order moment, and that interacts with the electric field gradient. So remember, dipoles interact with electric fields, and quadrupoles interact with electric field gradients from multiple expansions. So, and in the molecule, there's plenty of electric field gradient, because think about, for example, point charge, 1 over r squared. So the gradient goes over 1 over r cubed and blows up near the nucleus, right? So there's a huge electric field gradient near the nucleus. And this quadrupole nucleus feels it and interacts with it, right? And it causes an energy shift in the energy of the nucleus. So okay, so from the angular momentum point of view, you just have to write this out as a tensor product of two, rank tensors, second rank. You see this V sub I describes the electric field gradient, which is just undergrad EMM, just derivative of electric field with respect to R, right? And then the other one describes electric quadrupole moment, also there are multiple expressions. So it's but interestingly, you see this theta p, phi p, they depend on the, it kind of like internal nuclear coordinates, which makes sense because the quadrupole moment of the nucleus, it depends on how protons and neutrons are distributed inside the nucleus. And it's quite interesting because, right, molecule seems to know there's interaction that tells you about the structure of the nucleus in the molecule, which by measuring the energy shifts of, for example, due to this electric quadrupole moment and quadrupole interaction, you can actually learn something about the nucleus that's making up the molecule, right? So that's actually quite interesting. So you're doing nuclear physics with molecules. And that's what's wonderful about molecules. You're thinking you're maybe solving molecular structure problem, but you're actually going much deeper and solving problems from other. It has connections to other areas of physics.
This is different from atoms. Because atoms, the nucleus.
You can have quadrupole. Yes, I think. No, I don't think that's different from atoms. You can also have that in atoms. In rubidium, I think you can have. Yeah. Okay, atomic physics is also very important. Yeah. Right. But, so in this case, I'm going to rewrite it in terms of so-called tensor products. So the point of the slide is not to scare you, but to actually give you some more details about how these calculations are actually done, and maybe give you an idea what is the life of theorists. What we're dealing on a daily basis, right? So we write the Hamiltonians like this. Then we say, okay, what is tensor, like scalar product, dot product of two tensors? Can be written like that. And VI and QI is the components of the tensor. It's a rank 2 tensor, right? So it's like a matrix, symmetric matrix. And then you see, you actually define this electric quadrupole tensor as a second rank tensor product of two nuclear spins, right? On that nuclear spins operator sitting on the same nuclei, because it's a matrix, it has to be a kind of like tensor product of two vectors, right? To form a matrix, you have to tensor two vectors, right? Because it has to be a rank 2 quadrupole moment. So, and then you have your gradient of electric field, and then you form the so-called tensor product of two spherical tensors. And I think John covered that already. Or you haven't. It's basically you have two simple tensors, and you're trying to make a more complicated tensor out of them. So the way you do it, John did cover the Clebsch-Gordon coefficient. So you see these angular brackets. It's precisely what John mentioned in his lecture. So you have to actually combine those components with proper weights, which are Clebsch-Gordon coefficients, and into this tensor product, which is basically a super tensor. if you will. So it's just going to describe the interaction between tensors. Yes.
What is the rank of tensor A here?
1.
Where is that written?
Well, you kind of
It's
assume.
rotation.
Well, it's a vector. It's a rank 1 tensor. A is like slanted. All faces typically reserved for vectors. So we kind of know that it's rank 1.
Okay, so what if it were a second rank tensor?
Well, then you would probably not know. I don't know. We are being picky, yeah, nitpicky. But sure. So you can make even more complicated tensors out of this rank tensor. You can make 10th rank tensor, right? Life is complicated, right? So, but in this case, what I'm gonna show you is how we go about calculating the matrix elements of this thing, because this is what matters in practical calculations. Oftentimes, I give you the Hamiltonian, and you're interested in calculating the energy levels, right? How do you do the calculation of energy levels in practice? Well, you write down this Hamiltonian, and now in tensor form, it's extremely transparent. So it has the spherical harmonics, which are renormalized. It's C2P is a spherical harmonic, just in the frame, in the space fixed frame, and theta and phi describe the orientation of molecular axis in the space fixed frame. And then there's a couple of nuclear spins sitting on each nuclei, and then you have to sum you sum over nuclear spins and you sum over components of each nuclear spin, which is P. P is like 1, 2, 3, or X, Y, Z. Or 0 plus minus 1, depending on the theory. So now, once you have your interaction, right? You have your interaction, you nailed it down. So how do I figure out the shifts? Well, I have to define a basis set, right? And in the case of molecules, typically the basis set are used. The easiest one that I recommend is fully uncoupled basis set, which is basically a tensor product of rotational degrees of freedom times nuclear spin degrees of freedom, right? Each nuclear spin's got its own ket function, I m sub I, right? So because there are 2 spins in KRB, non-zero spins, nuclear spins, there is 2 ket there. So there's like 3 angular momentum, right? And if you want to be fancy, you can define a coupled basis set. You can couple nuclear spins, but sometimes it's advantageous. But in this particular case, I don't see any advantage to that. So I just wrote it down, because sometimes people want to show that they know angular momentum algebra and they use some fancy basis set. And I hate that when there is no need for that. But so I recommend using just simple, plain, uncoupled basis, because you can trace out all the terms and then you can write them down nicely. Okay, matrix elements, we'll be calculating them in a second, but you will need something also that's called the Wigner-Eckert theorem, which I'm sure John also mentioned, maybe in passing.
I did not wish that.
All right, okay. So if you have this matrix elements of any tensor in a basis with sharp angular momentum states, which is Jm. So it turns out then the dependence on M on the angular momentum projection on some axis can be factored out in that 3J symbol. And what is left is actually just a remnant, which is a so-called reduced matrix element, which describes the most important physics of the problem. And whereas the geometry or the orientation of the angular momentum is described by this 3J symbol. Right. So all the M dependence for both initial and final states can be completely is completely contained in the 3D system. So it's extremely useful, and we'll see that in a second. How do we go about calculating? Well, what we have to do, we have to calculate the matrix element of this non-NEQ nuclear electric quadrupole between the different basis functions. And this is how everyday life works is for theorists. You write down something like this, right? So you have this interaction sandwiched between the different basis states, basis kets. What you recognize, and that's actually the advantage of using the uncoupled basis set, is that the different terms in the Hamiltonian, they depend on different degrees of freedom, right? For example, this C2P depends only on rotation, right? Because molecules with theta and phi are rotating. So it only couples with rotational basis function, right? So you write it down as your NMN is rotational bra function, and prime is rotational ket. And they immediately go and form their own matrix elements with this spherical harmonic C2P, right? That's it. And the rest, so the problem factorizes into rotational part times nuclear spin part, right? And the nuclear spin part is just the matrix element over uncoupled spin 1, spin 2 times the standard interaction. that we already know is part of the NAQ nuclear electric protocol interaction. So you wrote the sum and you almost have that, right? So all you have to do is actually calculate the matrix element of rotational part and of the nuclear spin, right? So to deal with the rotational part, you just use the Wigner-Eckert theory, right? Because it has a matrix element with, as we discussed, Jm, J prime and prime, all projections. So all the physics is contained in this reduced matrix element, Y sub 2, and then there's a 3J symbol multiplying it, which depends on the projection of rotational angle momentum. So you figure that out, and now you are left with determining the reduced matrix element, but that you can just look it up and there. So these matrix elements are available. They're just another 3J symbol to be. So you put it all together, and then your matrix elements looks like this. Right? It's just a product of two 3J symbols times some normalization. It depends on initial and final rotational angle momentum. So it's not that complicated, right? Okay, rotations. We're done with rotations. So all we have to do is actually figure out the spin. Well, again, here one important thing observation is that because we have two nuclear spins, right? But the nuclear electric quadrupole interaction actually depends on induction of the electric gradient on each of the nuclei. So there are two terms. It depends on the spin of nuclear one, depends on the spin of the second nucleus, right? The first and the second. So we just here consider the first one, right? But there will be a corresponding term due to the second nucleus. But you see, the first nucleus only couples, only has non-zero matrix elements, in the basis set of the first nuclear spin angular momentum. So I1, M sub I1, has non-zero elements with this tensor offered inside the matrix element. Whereas it's completely diagonal in the second nuclear spin, because the first nuclear spin interaction is localized on the first spin, it doesn't care about the second spin. Right? So there's a Kronecker delta there, right? And then there is a matrix element that's left for you, it's just matrix elements, again, using Wigner-Eckert theorem, you reduce it to a reduced matrix element. And then you can be lucky if you have a really good, it depends on how good of an elemental book you have. Actually, this particular reduced matrix elements cannot be found in the book. You require a more serious tool. And there is a book by Vershalovich, the Russian astronomer, actually, in the 70s, he wrote a book, which is the most complete book on angular momentum. It's been translated into English. And there you have thousands of expressions like that. So good luck finding them. I found that for you. So it's inverse 3J symbol. Actually, it's kind of interesting. So this matrix element, but you don't have to, right? But it's just look it up. It's actually 1 over that particular 3J symbol with 2 in the middle, right? So you look it up and you put it all together, right? Now you have all the matrix elements that are there for you. You just have to put them all together. When you do, you end up with an expression. You see this in between the square brackets, which is very satisfying. It has all the rotations in it. It has nuclear spins in it, and it has this EQQ. EQ, little q, capital Q is the strength of the electric nuclear quadrupole at that particular nucleus. This kind of constant is typically measured in spectroscopic rotational spectroscopy. So they're also calculated. So you can find them for any molecule, and for KRB they have been actually measured and calculated, and you can easily find them. So you've assembled all of that. So all you do is just program that, right, using some basis, and then diagonalize your matrix, and then here you go. You get all the energy levels, right? This just goes to show that it's not hard to calculate the energy levels. You just have to be consistent, look up the correct Hamiltonian, and apply the right angular momentum theory, right? So, there's another couple of terms. I think, how much time do I have? Anyone knows? Hossein is probably. How much time do I have, Hossein?
12 minutes.
12 minutes. Okay, thank you.
I was a little bit lost. So what did you calculate? You calculated the nuclear electric quadrupole
matrix element of the electric ENQ
And
interaction.
what is the result now? We have a huge equation.
Yes.
What does it mean?
Well, it means that we have finished the calculation. Yes. Okay, so there you can get some insight for the reason of, I was, there's shortage of time. But for example, one insight you can get from this equation, it couples different rotational states. there's a coupling between n equal to 0 and n equal to 2. So n equal to 0, n is not a good quantum number in single molecules. Never. There's a very, if you just calculate diagonalization, there's a very, very small mixture of n equal to 2 and any n equal to 0. Due to this interaction.
Due to the electrical.
Yes, due to the, that's one insight you get. Second,
We have expected intuitively.
yes, probably because there is
That's the equation, that's clear, but.
well, but yeah, it is exact equation, it shows you, right? So it's not, you cannot dispute it. It's
So how big is the effect?
in KRB, I'm going to show you in one of the 2-3 slides. So but before, like we're done with KRB, we're not completely done with KRB because there was a question about magnetic dipole-dipole interaction. Remember two of them? Yes. Oh, yes.
Can I
Okay.
ask a question? Yeah, thanks.
Go ahead.
So I guess to summarize a bit what you said, so would I think everything here is like all these are sort of geometric factor and like even the reduced matrix element, you can find formula, and the only thing that's ab initio or experimentally measured is the EQQ. Is that right?
Yes, that is correct. So in this expression, you see, it only depends on the EQQ constant. Yeah, and of course, nuclear spin values of the nuclei.
You see what are these constants? What is E, what is Q, what is contact?
E is the charge of the electron, and QQ is this Q is the charge of the proton, I think, and capital Q is this, right? Protocol coupling. Yeah.
So it's the big Q is the ab initio or experimentally measured.
Yeah, the big Q is the one that's comes from gradient of electric field and stuff. So you can break it down because the actually no, yeah. In hydrogen atom, I can tell you, but in the molecule, gradients of electric field are not so easy to compute, right? So.
And also just a quick question. So is everything else, I mean, like you found this formula in this book, but like, can I just somehow find everything or ask Mathematica to give me?
Yeah, totally. You can just plug it in Mathematica or Python or your favorite, programming language. And like I use Fortran.
I mean, like not even breaking. Like I know Mathematica has 3J symbol, but I mean beyond that, like the reduced matrix element, like it has that.
Oh, no. That maybe there is like a newest version of Mathematica, but usually these expressions are so obscure. So for example, like this one, like with 3J symbol to the power of -1. This one is rare. So I think the only like just looking it up, it would be better strategy. Yeah.
Okay, thank you.
Yeah. Okay, so we're only, I mean, I'm sure you guys are tired of all these interactions. So I'm going to be quick. So this is just magnetic dipole-dipole interaction. And we transformed it, I think John already mentioned, we can transform it to a space fixed frame where it assumes a second rank tensor form, coupled with a second order spherical harmonic. And there's also direct spin-spin interaction because spins feel each other through the electron density distribution because the molecule, they interact with electrons and then the electrons interact with the other spins. So this is, through the electron density interaction. So C4, actually it's very small, but it's non-zero. So we're going to go through these relatives magnitudes, in 2 slides. And finally, I just want to mention the Zeeman interaction. So the Zeeman term has 2 main components. One is the interaction of rotation with magnetic field. And then each of the nuclear spins also interacts with magnetic field, right? Because it's a tiny dipole, magnetic dipole. So what is interesting is that this interaction is not the one that you would expect for free nuclear spins, because they're sitting in electron density distribution. The magnetic field is imposed on them like externally, right, in the lab. But they also have electrons which shield them from interaction. They cannot fully interact, in other words, with magnetic fields because electrons are canceling those interactions to some extent. And this is called magnetic shielding. And this constants, sigma alpha, they're called magnetic shielding constants, and they depend on the details of electron distributions in the molecule, right? How electrons are behaving in the molecule, and that's how effectively they shield off the external magnetic field. And that's used in NMR for chemistry a lot because, I mean, you can measure those, and these coupling constants or shielding constants, they tell you something about the chemical structure of the molecule and the electron density distribution, right? That's the whole point of using NMR in chemistry, by the way. Well, there's much more, but this is kind of one of the big things that you can measure that tells you about. For example, benzene will have one kind of sigma alpha, and like naphthalene will have another type of sigma, another value. So by measuring that carefully, you can actually distinguish between different chemical species. So other terms, diamagnetic Zeeman term, we're not touching here because they are typically very small and the second order in magnetic field and become important only at very large. So now on to, very quickly, I don't have a lot of time. This is the energy levels of KRB, okay? So people ask questions about what is the relative magnitude of different interaction. So in n equal to 0 ground rotational states, you can show there's no diagonal element or shift due to the ENQ interaction, electrical quadrupole. Because of that, all the shifts are due to the spin-spin interactions of tensor and direct. Turns out the direct has the largest contribution, but this contribution you see is about 0.05 megahertz. So the shifts are in about like tens of kilohertz, something like that. That's kind of the shifts you expect due to nuclear spins in the ground rotational states. However, in the first excited rotational state, things change completely because that's when nuclear electric quadrupole interaction starts to enters the picture and induces large shifts, right? It shifts different rotational states by up to, you see, it's 0.4 megahertz. So it's quite a substantial energy shift. And it actually completely restructures the energy levels at weak magnetic fields. And you need to apply at least, you see 60 Gauss, it's about 100 on the right hand side, on the right edge of that plot. So even at 100 Gauss, you are not completely decoupled in the ground, in the first excited rotational states. The spins are not, they're talking more, they're coupled more by this nuclear electric quadrupole interactions. They are, decoupled by the magnetic field. So in a way, this is similar if you're atomic physicist. So this is similar to the Paschen-Bach effect in atoms, right? When you apply very strong magnetic field, the spins like to precess around the magnetic field. So they're being torn apart from precession about their other angular momentum and the natural precess about the external magnetic field. But for that, you have to apply a significant magnetic field, typically. And here, this field can be, to fully decouple rotational excited state, that could be like 500 to 600 Gauss. And you can actually, to be like precise, you can never decouple it fully because there will always be a small contribution due to the electric quadrupole that couples different speeds. Even if you have 1 Tesla, it would just be very small. Okay, so how do I understand the structure at small magnetic field? Actually, the total angular momentum of the molecule is conserved at 0 field, right? So we know that. So we can actually use that to our advantage. We define the total angular momentum as a sum of rotational angular momentum and the nuclear spins of the 2 nuclei in KRB. And you see that n equal to 0, for example, I1 in KRB is, I think it's 4, right? And the other is 3. So at least in the KRB molecule, the fermionic molecule that was made at G, I think also at product, right? It's 40K 87 to be divided. So it's 4 and 3/2. So you get a range of F values, right? Using the angular momentum addition rules because it ranges from I1 minus I2 all the way to I1 plus I2 for ground rotational states. And therefore, you see these little manifolds in the 0, they actually can be labeled by the value of total angular momentum. Right. So, and the same happens for the rotational excited state. It's just you have to add 1 more unit of angular momentum due to molecular rotation. Right. And you can understand that this nuclear electric quadrupole interaction is splitting very well.
So for 0 magnetic field, please explain to someone who's not so familiar with this.
Yeah.
If it's a normal magnetic field 0, let's say, spin interaction, that what we say, why does it have 4 levels? I mean, many levels, but coming 4 manifolds. No?
Yeah.
So there are 2 spins. And
yeah. One is 4 and the other is 3. No, I think it's nuclear spin 4.
Nuclear spin.
Yes, nuclear spin 4. And rubidium has nuclear spin 1. That particular isotope that's shown in this plot. So 4 and 3/2, they give you.
Okay, that's what I want.
Yeah, the electron spin is 0. Yeah. Yeah. So, okay. So 36 nuclear spin states in just the ground rotational manifold, right? That's an amazing number of states. So very quickly, summary for, no summary here. just for, I think we're just moving on to double sigma molecules, but I have very little time. So like the only difference between single sigma and double sigma molecules is because in double sigma molecules, you have one additional electron spin, right? Spin 1/2 that's sitting on some orbital, right? And sigma molecule means like it's a sigma orbital. So it's symmetric under transformation, like angular momentum, or like rotation around the molecular axis. So why are these molecules important? Because they're typically laser coolable molecules, and actually calcium fluoride, strontium fluoride, and yttrium oxide have all been laser cooled and trapped at many laboratories already. So an interesting thing here is that electric and magnetic dipole moments can now interplay, right? And his very interesting physics that is not available in single sigma molecules. And the only really new interesting interaction, now U-term here in double sigma molecules, you have the spin rotation interaction. And spin rotation interaction is like n dot s. The spin couples to molecular rotation. And simply understood, like rotation creates a magnetic field that interacts with the electrics, with the spin, right? But if you want to go to more detailed description of this interaction, you have to consider relativistic effects. Gamma is typically below 0.01 wave numbers. So it's a very small interaction, but it nevertheless plays an important role in spectroscopy and collisions of double sigma molecules. So again, hyperfine structure. Now the same old story with magnetic dipole interaction, except that now we have nuclear spin and the other spin is like 1800 times stronger because it's like electron spin. So the interaction is substantially stronger, 3 orders of magnitude, but it's still magnetic dipole interaction. The one interesting twist here is we have now Fermi compact interaction, which is kind of not present in single sigma molecules, but here electrons in s orbitals, they can actually they can penetrate and access the nuclei. And they have non-zero density probability of being at the nucleus. And near the nucleus, as we know, the magnetic field is very different from near the proton, for example, hydrogen, very different from typical magnetic dipole distribution, right? It's actually created by nucleus, right? And that's another way the nuclear structure actually enters molecular spectroscopy and atomic spectroscopy through the Fermi contact interaction. So this is two kind of new interactions that we have. And in Zeeman structure, the only new thing here really is B dot S is not really your atomic B dot S, but G sub S is actually a 3x3 matrix, it's a tensor, so-called G tensor. And this G tensor is anisotropic generally, but in diatomic molecules, no one cares about it. So people throw it away and they say, oh, it's just like diagonal matrix times the G factor of the electron. But in polyatomic molecules, people actually care a lot, especially electron spin resonance spectroscopy. They measure these G matrices all the time. Okay, so again, a typical structure here in double sigma molecule, like this is a plot for yttrium oxide, was actually laser cooled and actually trapped in optical lattice, I think, at Gila recently. So levels in n equal to 0 and n equal to 1 rotational manifolds, they experience Zeeman shifts. And actually from far away, the Zeeman shifts look almost the same because they're all determined by the magnetic field interaction with electron spin, right? And this tiny splittings you see, they're due to the fine and hyperfine. And hyperfine hyperfine acts kind of across the board. It shifts all the states, all the rotational states, but the spin rotation / fine interaction only shifts rotational excited states, which are n greater than 1 or equal to 1. And you see what is interesting is that in double sigma molecules, there's a new feature here, is that because of this rotational states have certain splittings, the rotational states of n equal to 0 and 1 of the opposite parity, actually they have parity, they cross. You can actually engineer a magnetic field where you can make these states nearly degenerate. And when you do that, this is actually impossible to do almost with atoms. You cannot do that with normal kind of atoms, like alkaline atoms or earth atoms that people use in all physics. So this degeneracy is actually quite interesting because they're kind of uniquely molecular features of single molecule degeneracies. And one example is recent paper that came out of the Harvard MIT Center for Electrical Atoms, where collisions of sodium lithium molecules were actually strongly affected near this degeneracy point. And in that experiment, magnetic field was tuned near degeneracy, single molecule degeneracy in sodium lithium molecule, and collisional rays experienced a sharp spike. that was actually we attributed to a magnetic resonance, which is actually a new molecular resonance that exists just because of that degeneracy. You cannot explain the resonance if you do not involve the concept of degeneracy. So this is just one example where qualitatively new effects arise in molecules induced by uniquely molecular features that atoms don't have, or it's extremely difficult to engineer in atoms. In molecules, you see how many degeneracies? Pick your own degeneracies. There's like hundreds of them. Okay, so my conclusions for today is molecules are great. They have complex interactions that can lead to patterns of energy levels that do not exist or extremely rare in atoms. So pretty much any interaction that you can dream of or think of, there is a problem molecule that have that's a blessing and a curse. Blessing because we can pick a molecule and realize whatever we want. A curse that we have to understand a lot of things that we didn't have to understand in atomic physics. So what else? Well, angular momentum techniques are useful. So, and I hope I made it a little bit like less mysterious, the process of calculating molecular energy levels. So, thank you for your attention.
Graph that you showed, the MEQ interaction only causes splitting for the one manifold. Why is that?
It's in this matrix element, which I know. I'm sorry, you don't. Probably I should stop sharing here and then share again. I don't know, but the matrix element has n2 n prime 0 0 0. If you remember of the electron protocol. And if n is equal to 0 and n prime is equal to 0, you get the matrix element is proportional to this matrix, and that is 0 because triangular division is binary, right? You cannot add 0 and 0. So therefore, mathematically it's 0, but physically it's just spherically symmetric distribution of when you integrate something anisotropic, which is electroprotocol interaction over spherical symmetric distribution, you get 0.
That means it shows up for n equals 1, or does it show up like, I guess what
it actually shows up in any n greater than 1. Because you see this matrix element is non-zero for any n greater than, if n prime is equal to n and greater than 1, you will have it. Right? Because actually it compensates with n different by 2. So there's both diagonal and diagonal.
Can you elaborate a little bit more on the last, like we showed the Soviet experiment?
Yeah.
So you mentioned that it's the same mechanism at the avoid crossing for input 0. What thing for Soviet experiment? The collisions to one instead of
yes. Yes. So when you're near the genus, channels that are existing near the but that's a topic of research, right? So and it turns out that decay into the states is very sensitive to the energy gap between energy levels. It's just like a feature of pressure compare, this phenomenon, which we're not really talking. Turns out decay is very sensitive to this, and typically it happens delta is very large. So people just actually overview the sphere just see the delta to infinity is large. So and what we did was just like shrink it down to 0 for the shoulder. Turns out the decay mechanism is dramatically changed with the level of energy. And because of that, there is a resonance.
You say you make the same
The genus.
molecule energy.
Yes, single molecule energy is when they're in the genus, right? In when you don't have the genus.
That's already on the basket.
No, it's not a bounce effect. Because it's unique, like it's a new mechanism.
due to the changes. And people like couldn't see the analysis because I mean, you cannot have that analysis other than some exotic conditions frozen to make it. But normal alkaline metals will not be dangerous. In single sigma molecules, if you can have the Jers, then why not? But there are some conditions we actually talk about them in the paper that, for example, nuclear spins they have to match. So the nuclear spins have to have a zero overlap. No, probably there won't be but so a necessary condition, but not constant. So you need to have no zero overlap to nuclear spins because otherwise the interaction potential will stop with things. Right? They have to be coupled by the interaction potential, which we'll talk about in lecture 2. But yeah, but in fact, to be honest, it's still a mystery because there's some other processes where also nuclear spin overlap, but there was no resonance. The calculation that you showed us are wonderful, but somehow complex. There are people saying that a quantum computer maybe once with this can be of help. Can do this for you. Do you agree with that? Oh, sure. I would love to have a quantum computer helping me out. Would it be able to use these kind of calculations to that you showed us? Oh, these calculations are, I mean, they can be done on the level. They are simple because the number of states that you is below 1,000. But once you start about 2 molecules, that's where the problem becomes rapidly from easily tractable to impossible. Yeah, because it's a 4-body. Exactly. So, and therefore, that's it. I mean, no classical computer can presently solve, let's say, 2 sodium lithium molecules in a magnetic field. So much less KRB. So we'll have to wait either for quantum algorithms. We are developing some in our groups, so we can talk about that, for scattering problems, but also for maybe very efficient classical algorithms can be developed for this kind of problems. Still an open question, which if we have a quantum advantage or not, it's eventually it depends on how efficient your algorithm is.
More questions? If not, then join me in thanking Timur for a very useful track our way down, and down is walking toward the steps.
We can all gather at the up there and then go down.